This lesson starts our discussion of differential equations, our new unit. And in this particular unit, we're going to learn how to visualize solutions and approximate solutions to differential equations. We're going to learn how to solve some separable differential equations using a separation of variables, and then we'll look at how to solve some particular kinds of differential equations involving population growth and decay. All right, if you choose a career path involving STEM, chances are in college you'll have to take a separate differential equations class. It's definitely going to go a lot deeper than what we're going to do here. So we're going to start off with slope fields and Euler's method, and there's two objectives here. The first one, use slope fields to approximate solutions of differential equations. In general, differential equations are pretty tough to solve. So the slope fields gives us a way to visualize what a solution could possibly look like, given that I can't actually find that particular solution. The second objective is exclusive to BC. This is a BC only topic. We're using Euler's method to approximate solutions to differential equations. And as we'll see, this is going to be sort of like a course correction. I've gone on some sort of path, and then a little bit along the way, I'm going to have to veer to the left or to the right. I got to course correct. That's what Euler's method is very similar to. Before we get started on the content of this lesson, let's take a look at the web, shall we? All right. I'm going to suggest that you print out at least one thing here from my website. To get here directly, we're going to go to the Calculus tab, and we are in, it says Unit 8 here for differential equations. If I tap on that one, it's the very first one, 8.1 slope fields in Euler's method. If I scroll down just a little bit, there's the lesson notes and the answers, and here's the worksheet that I'm particularly talking about, this one here, that if you have access to a printer and you print that out, it might make a part of this lesson a little bit easier for you to work on. Otherwise, you're going to have to draw all those dots by hand. Okay, here is part of the homework. There's the usual AP practice problems, and the answers go along with it. Scroll down just a little bit more. If you have your own TI calculator, you can download these programs, not directly to your calculator, of course. That'd be weird, because that would be sort of modern. Anyway, you have to download them to your computer and then transfer them to your calculator using a program called TI Connect. One's on slope fields and one's on Euler's method. And then you scroll down just a little bit more, and here's another worksheet that you should probably print out, again, if you have access to the printer, and that's this slope fields homework sheet. It just has a nice printout of these slope fields. This is what they look like. That's going to help you draw some of your homework questions, okay? All right, so let's go back to the actual lesson here and take a look at our warm-up question. Show that y equals e to the negative 2x satisfies y prime plus 2y is equal to 0. So what we have right here is a differential equation. It has a y prime in it, and it's got two y's in it. It's a differential equation that involves just y's. And then we think that y equals e to the negative 2x is a solution to that differential equation, and it's pretty easy to check. All we have to do is take y prime plus 2 times y, plug it into that equation, and see if it's equal to 0. So let's try this. So our differential equation here is asking us for the derivative of y. So that's what I'm going to do first. I'm going to take y prime should be equal to, well, this is exponential. Anything exponential is its own derivative. And then I have to use the chain rule because negative 2x is a composite function. It's stuck inside of the exponential. So I multiply it times the derivative of the interior, which is negative 2. And maybe we would have noticed that right off the bat and just went, hey, it's negative 2 e to the negative 2x. Okay, so now what I'm going to do is I'm going to take this as the derivative, stick it in there, take this as y and stick it in here, and it should equal 0 when I'm all done. So y prime is negative 2 e to the negative 2x plus 2 times my original y, which is e to the negative 2x, and indeed that is equal to 0, which means that this is a solution to this differential equation. And this one we could solve. This one is separable, and in the next lesson we'll learn how to actually solve it, but they're not always going to be quite as straightforward and easy as that one was. Okay, so let's take a look at the slide for this one, the picture. And in this picture, this looks sort of like what we're going to call slope fields. You're going to be able to use slope fields to approximate solutions of differential equations because, again, sometimes they're kind of tough to solve. The picture here, picture of some gravity waves and electromagnetic fields, all of those things look very similar to slope fields. And say currents in an ocean, something like that, currents in a stream. So differential equation in x and y is an equation that involves x's, y's, and then derivatives of y's. And we've seen some very simple ones like this one, y prime is equal to x plus 3. And if I wanted to work that thing backwards to get y, that's this act of solving a differential equation to get y. What's the original equation? That is integration, indefinite integration anyway, or anti-differentiation, right? So I take its integral, and this one has a little plus 1 at the end, so this must be some sort of particular solution. We must have had some initial condition that we could have used to solve it. And then, of course, we could take the derivative of that and get back to that differential equation. Very, very simple one, and so far that's about as far as we've taken differential equations, okay? So y equals f of x is considered a solution of a differential equation if y and its derivatives satisfy that differential equation. So all of these are examples of solutions to the differential equation y prime is equal to x plus 3 because all this recipe is just asking you to take the derivative of each one of those equations and it should be equal to x plus 3. Okay, each one of these is a particular solution given some initial condition. The general solution, of course, is the one that has that plus c in it, which is the constant of integration. It allows us to maybe move this thing, in this case, moving this thing up or down. And we're going to see that's not the only thing that's possible. We can also have some other kind of transformations that are happening there. Okay, so we've got some different kinds of differential equations. We're going to be looking at both first-order differential equations and second-order differential equations. And the order of a differential equation simply refers to the highest order of derivative within that equation. Does it have a first derivative? Does it have a second derivative? The ones over here on the right-hand side of the screen, these are first-order differential equations. We just saw this one right here. Whoa, hey, no, that's not what you're supposed to do. We just saw this one. All right, we just worked on this one. The very next one, this is exponential growth and decay. This one is for both AB and BC. The one underneath it, this is logarithmic growth, and this is only for BC. If I look over here on the left side of the slide, I've got some second-order differential equations because I got some second derivatives in the picture. This first one, y prime is equal to negative 32. This one is the acceleration due to gravity. Right up above it, this m d2y over dx2 is equal to negative kx. That one is Hooke's law. It's a second order differential equation. And then the one that's right up above here, it has some second derivatives in it, but these are partial derivatives. Again, this is something that you would do in a diff EQ class, but not in this one. All right, so in this first example, we're going to do exactly what we did on the previous warm-up question, is we're just going to check to see if each one of these is a solution to the differential equation y double prime minus y is equal to 0. So here we've got ourselves a second order differential equation because it has a y double prime in it. So let me scooch down right in here. So this is telling me that I need two derivatives and I also need the original equation. That should be pretty easy for each one of these functions. So y prime is equal to a cosine x. Y double prime is equal to derivative cosine is negative sine x. And now I'm just going to plug both of these things into this differential equation, see if it's equal to 0. So y double prime is negative sine x minus my y, the original y is sine x. That is not equal to 0. As a matter of fact, it's equal to negative 2 sine x. So this means that this is not a solution to that differential equation. Nope, not going to do it. All right, let's take a look at number 2. We've got y is equal to 4e to the negative x. So y prime is equal to negative 4e to the negative x. That negative is part of the chain rule part of this. Second derivative, that negative will cancel back out and go back to 4e to the negative x. And now put them in our differential equation. We've got y double prime is 4e to the negative x minus the original y, which is exactly the same thing. Subtract that, definitely equal to 0. So yes, this one is a solution to that differential equation. All right, let's look at the last one. Y is equal to c e to the x. The c in this case is some sort of constant. It could be 2, 17, pi, whatever. Y prime is equal to c e to the x. Y double prime is c e to the x. There we go. And then plugging these into the differential equation, whoop, c e to the x minus c e to the x is definitely equal to 0. That checks out. Wonderful. So yes, this one is also a solution. So a differential equation can have lots and lots of different solutions. And our first objective is going to be how we can visualize what those solutions could possibly look like. Okay, example 2. Show that y is equal to e to the 2x minus e to the 3x plus x e to the 3x is a solution to the second order differential equation, and you can see it right here. Y double prime minus 5y prime plus 6y is equal to e to the 3x. Whew, man, what a jump from the things that we saw on example 1 to this one here. All right, shouldn't be a problem. So notice I need 2 derivatives. I need both y and y prime, or y prime and y double prime. And I also need to change back to blue. It's official. Y prime is equal to 2e to the 2x. I'm taking the derivative of this original equation here. Minus 3e to the 3x. Plus, and then I'll have to use the product rule on this one. The derivative of the first is 1 times e to the 3x plus the first one, x, times the derivative of the second one, which is 3e to the 3x. So this is 3x e to the 3x. And notice I've got some like terms here. I can combine those up. 2e to the 2x, negative 3 of them plus 1 more is negative 2e to the 3x plus 3x e to the 3x. Okay, so now we're going to take the second derivative of this one. 2e to the 2x, its derivative is going to be 2 times that, so 4e to the 2x, minus, and I'll have this 3 that's going to multiply times the 2, 6e to the 3x, and then we'll have to use the product rule one more time on this one, plus derivative of the first is just 3e to the 3x, and then the second one is going to be 3x times the derivative of e to the 3x. The 3's will multiply 9x e to the 3x. And then again, we have some like terms to combine. 4e to the 2x minus 3e to the 3x plus 9x e to the 3x. All right, so I'm going to take both of these things, this and that, and put it into this second order differential equation. And hopefully it's going to simplify down to e to the 3x. Hopefully. Okay, y double prime, just write it down. 2e, 4e to the 2x minus 3e to the 3x plus 9x e to the 3x. All right, so that first part is good. Minus 5 parentheses times the first derivative, which is 2e to the 2x minus 2e to the 3x and 3x e to the 3x. And then finally plus 6 times the original equation, e to the 2x minus e to the 3x plus x e to the 3x equals question mark e to the 3x. That's what we're going to check. Okay. And then combining some like terms, so I'll have to rewrite some stuff right here. Copying down this first part. Distributing the negative 5 through this is a negative 10 e to the 2x, positive 10 e to the 3x, minus 15x e to the 3x. Now distributing the 6 through this, 6 e to the 2x, minus 6 e to the 3x, and plus 6x e to the 3x. Again, is that equal to e to the 3x? All right, let's see what we've got. We've got these and this one and this one. We've got 6 plus 4 gives us 10 minus the 10. All of those e to the 2x's cancel out. All right, let's look at the e to the 3x's. I've got negative 3 of them, positive 10 of them, and a negative 6 of them. So the negative 6 and the negative 3 makes negative 9 of them, plus positive 10 gives me 1 e to the 3x, just one of them. So far, so good. So apparently everything else is supposed to cancel out. So let's see. Maybe this one should be green. We got 9 of them, minus 15, plus 6 of them. So 6 and 9 gives us positive 15, and the negative 15 cancels out. So it does indeed equal e to the 3x. Ta-da! So y equals e to the 2x minus e to the 3x plus x e to the 3x is indeed a solution to that second order differential equation. All right, so when we come back, notice that we haven't actually looked at any slope fields yet. Let's rectify that.